All right, so welcome back. Let's do one more example for angular momentum. So let's see what's given to us in this problem here. So we have a mass of 2 kilograms and 20 centimeter diameter turntable. So that's the diameter, meaning you can find the radius will be 10 centimeters. It rotates at an omega of 100 RPM on a frictionless bearing. So I'm going to try to put a picture together here. Okay, remember. Okay, so let's say this one turns about the center here. And there are some bearings here. They are frictionless. And then all of a sudden we have two masses, each one of 500 grams blocks. They fall from above and they hit the turntable. So let's say here is mass 1 and mass 2. They are identical. I'm just going to call them M, I guess. We're going to call this one capital M just to keep it all straight here. So they fall from above, and so they stick based on what it says. So here we have the masses stuck at the end here. All right, and this system is now going to slow down probably. So I'm going to call this phase 1, and here's phase 2, right? So we can actually depict the situation. So they hit the turntable simultaneously at the opposite end of the diameter. So this is what we've been doing here. Okay. And they stick. What is the turntable angular velocity in RPM just after this event? So essentially they ask you, hey, what is the omega 2, assuming that this is omega 1, after this happens? So essentially you are treating here everything as a rigid. So this is a rigid disk. Those are the ones that you already calculated the moment of inertia. That was 1/2 mr squared, if you remember that. And then essentially you have to looking at this problem, who conserves. So the two blocks that they are falling from above, now they create a new system once they stick. So now you have a new system where you have a distribution of mass equally distributed, however. But each one of these mass works like a particle, right? And they bring into the equation the new components on top of the disk. So essentially for this problem, you have a moment of inertia in phase 1 before the two blocks hit the turntable. And then you have a moment of inertia in phase 2, which will be equal to the moment of inertia of phase 1 plus whatever the two other particles are bringing into the picture. And then you have to think about the fact that the angular momentum here is conserved. So having said that, our angular momentum final equals to angular momentum initial, or actually I can say L2 equals to L1. Out of that, you kind of have to go backwards and find out what is I for each one, the moment of inertia. Doing then the conservation of angular momentum, we're going to find out what omega 2 is. So let's go about it. So first I'm going to focus on finding I1. I1 is pretty simple because we are talking about a solid disk. And this disk is spinning about the center. And this is 1/2 mr squared. And now we're going to plug in our numbers. The mass here is 2 kilograms. Okay, I'm going to put a unit this time, not only at the end. And then the radius is half of the 20, so that's 10 centimeters, so 0.10 squared, and these are meters squared. In the end, after you do the math here, you get, let's see, 0. So this goes away. So 0.0 0, 1, 0, and those are kilogram meter squared. All right, so we have the first inertia right there. Now let's see the moment of inertia final, which will be our I2. So that was our I1, plus whatever each mass brings into the equation, but each one of them, if you remember the general I, right, that was integral of r squared dm. Now in our case here, we don't have to integrate. It's everything nicely distributed about the center of mass. The radius is considered to be the same, and you have two additional particles with equal mass, so it will be plus mr squared plus another mr squared. So that's your 2mr squared, the contribution of the two blocks. So hence this becomes I1 0.010 kilograms meter square plus 2 times, these blocks were 500, so 0.500 kilograms times the radius square, same idea, the same radius, 0.10, and those were meters all squared. So after you plug everything together, let's see here, I am getting 0.020, and those are kilogram meter square. All right, so we got a before and after moment of inertia. Now you will have omega 1 and omega 2 for each one of those phases as final and initial angular velocity. So then now we can actually do the conservation of angular momentum. So let's see what this one derives to be. Or L2 equals L1. So that becomes omega 2 I2 equals omega 1 I1. Since from here you get omega 2 equals omega 1 times I1 over I2. All right. So now, how much is our omega? They don't even specify if you need to have this. Oh, they tell you in RPM. Okay. So you need to find that in RPM, meaning that we don't have to actually convert much. We're going to leave the omega 1, this is 1 actually, as 100 RPM. Okay, and I1 was 0.010. The other one is 0.020. These are, well, kilograms per kilogram simplifies out, so is meter square per meter square. Final answer, this, as you can see here, it's 50. And those are RPMs. All right, so this kind of concludes the basic examples from this chapter. I would like to do some more general problems, so that will be in the next video. Thank you.